Hi, Assalamualaikum and a very good morning. So today we're going to do some tutorial discussion for chapter 2, focusing on subtopic of 2.4 Born-Haber Cycle. We're going to do two questions, which is tutorial question 11 and tutorial question 13 respectively. So without any further ado, let us start. So for tutorial question 11, based on the data given below, which is the enthalpy of hydration of Na+, given as negative 390 kJ per mole, and the standard enthalpy of hydration of Cl-, which is negative 380 kJ per mole, and the standard enthalpy of solution, which is NaCl, equal to positive 6 kJ per mole. So we have to construct an energy cycle diagram to represent the dissolution of NaCl. Once we done the construction of energy cycle diagram, we have to calculate the lattice energy of the NaCl. Alright, so as what you have learned in lecture of part 2.4, the dissolution processes of NaCl can be gotten from the dissolution of ionic solid, NaCl, and it can be broken down into Na plus aqueous ion as well as the Cl minus aqueous ion. So this is a usual pathway or known as the pathway 1. Okay, and for the dissolution process, it can take another pathway, which is pathway number 2, which involves two steps. First, it's going to have enthalpy of lattice dissociation enthalpy, where the ionic solid will be broken down into gaseous ions first. Okay, where NaCl solid will be broken down into Na plus gaseous ion and Cl minus gaseous ion. And this is going to be hydrated in water so that the gaseous ion can be formed into aqueous ion for both the Na plus and Cl minus ions. Okay, so this is pathway number 2. And you know that in the enthalpy change of pathway 1 and pathway 2 will be the same. So this is covered in the lecture video. So let's do it again nicely here. Okay, so for the dissolution of NaCl, it involves ionic solid broken down in water in order to form Na plus aqueous ion and Cl minus ions. And this give an enthalpy of the solution of plus 6 kJ per mole. Alright, and as for the hydration, here it means that it comes from gaseous ions, for example, M plus ion, forming into M plus ion, but now in aqueous state. So this, you need to look back at the definition of hydration in the lecture video of 1.1 part 2. So hydration is the enthalpy change when 1 mole of species in the positive or negative ion in the gaseous state produced into aqueous ion here. Alright, so this will undertake path number 2, where NaCl ionic solid will absorb energy in order to dissociate it into gaseous ions. Okay, and NaCl solid will be broken down into Na plus gaseous ion and Cl minus gaseous ion, and this is known as the lattice dissociation enthalpy. Alright, and Na plus gaseous, as I mentioned here, will be hydrated under water in order to form Na plus aqueous. So we're going to make another arrow connecting these two. And the enthalpy of hydration of Na plus is equal to negative 390 kJ per mole. Meanwhile, the enthalpy of hydration of Cl minus ion of the gaseous into aqueous going to have negative 380 kJ per mole here. Alright, and as what you learned in Hess law, A going to C is the same as A going to B going to C. So the enthalpy change here gonna be the same. So you can say that A to C is the same as A going to B going to C, where the initial point to the final point. Okay, so the enthalpy change between them is the same. A going to C or A going to B going to C. So it can happen at one step or in a series of steps. So you can find delta dissociation enthalpy first, where the enthalpy of solution is known as 6. You can substitute that in. Dissociation lattice enthalpy is our unknown. Enthalpy of hydration of Na plus is negative 390. enthalpy of hydration of Cl minus is negative 380. So the dissociation lattice enthalpy gonna be positive 776 kilojoule per mole here. Okay, but remember, you have to find the lattice energy of NaCl, not lattice dissociation enthalpy. So it basically means that it needs to come from gaseous ion into solid, into ionic solid here. So it is to be in the reverse direction. So in order to find lattice enthalpy, we can get the same magnitude, but we just changes the sign here. All right. So the lattice enthalpy gonna be negative because we change sign and equal to 776 kilojoule per mole, where the magnitude is still maintained. All right. For tutorial question 13, we have to use the data below to construct a Born-Haber cycle for copper 2 oxide and determine its lattice energy. So the data is given here and you have to write the thermochemical equation and constructed a Born-Haber cycle. But in this video, I'm going to show you how to write in terms of the energy cycle method first, and later we're going to do the Born-Haber cycle. All right. So the first thing that you need to know is the enthalpy of formation of copper oxide. So the enthalpy of formation of copper oxide happens when 1 mole of substance is produced from its element. Okay, so copper oxide, it needs to be in the unit of 1 mole here. All right, so copper solid react with oxygen gas, which is here. And since it is in 1 mole, we couldn't change the number of mole here. We have to change everything in the reactant side. So one copper here, and half of oxygen is needed to ensure that the number of oxygen is 1 on both sides. So this one is in solid as well. Okay, so in order to write the energy cycle method and Born-Haber cycle, I usually start with the formation first. All right, and let's do that one first. So the enthalpy of formation of the copper oxide, which is from copper, and half of the oxygen in order to form 1 mole of copper oxide. And the enthalpy of formation is negative 115 kilojoule per mole. Now we have settled with this equation. Okay, now we proceed with the enthalpy of atomization of copper. So enthalpy of atomization of copper means that from a solid substance, it will be a gaseous substance. All right, and this require energy which is plus 339 kilojoule per mole. So let's do this one. From copper become copper gas, and this requires an enthalpy of positive 339 kilojoule per mole, where A refers to the enthalpy of atomization. All right, and we have done with this step. We move on to the next step, which is the first ionization energy of copper. So ionization energy means copper in the gaseous ion will remove 1 mole of electron in order to produce copper plus gaseous ion, and 1 mole of electron is being donated. So this requires energy which is 745 kilojoule per mole. Okay, now you do the same thing but for the second ionization energy, where the second ionization energy means it started up from a copper plus gaseous ion and it's going to produce copper 2 plus because it's a second ionization energy and remove another mole of electron. And this require energy as much as positive 1960 kilojoule per mole. All right. So from the first 3 or 4 steps here, you will realize that it is so important to know the thermochemical equation, and you need to be able to master to write the equation for the various enthalpies that we have learned in subtopic of 1.1 part 2. So enthalpy of atomization, enthalpy of formation, first electron affinity. So you need to be able to define and write the equation. All right. Now we look into the oxygen part. We have done with the copper. Now we look into oxygen. So enthalpy of atomization of oxygen. So oxygen, half oxygen, it's gonna be 1 mole of oxygen. Okay, and this gonna have a enthalpy value of 248, where Ha refers to atomization of oxygen. And now first electron affinity, it means that oxygen, which is in 1 mole of gas, receive 1 electron in order to form O minus. So this will release energy, which is negative 141 kilojoule per mole. All right, and for the second electron affinity means that the negative ion that has been produced will receive another electron in order to form O2 minus, and this will become second electron affinity. Okay, and this requires energy, which is positive 791 kilojoule per mole. So we have settled with these three things regarding the oxygen. And from the energy cycle method that we have constructed, we have to find the lattice energy, where lattice energy means from gaseous ions, for example, M plus ions and X minus ions, it need to be in the gas state, it need to form an ionic solid in the solid state. So we have to make another arrow here from the gaseous ion to form a solid state ion. Okay, and this is known as the lattice energy. All right, and the whole process here is known as the energy cycle method. All right, and in order to find the lattice energy, we need to remember our Hess law. Hess law states that the energy change is the same whether it takes one step or a series of steps. So you can say that A going to B, going to C, going to D, going to E is the same as A to E. Okay, so we can say that A going to E, which is the enthalpy of formation, is the same as A going to B, going to C, going to D, going to E. So as long as initial and the final is the same, means that the enthalpy change going to be the same. All right, so delta HF here, and then we add up is equal to HA of copper plus delta H of first ionization energy plus delta enthalpy change of second ionization energy plus enthalpy of atomization of oxygen, first electron affinity, and second electron affinity of oxygen plus the lattice enthalpy. Okay, so this one gonna equate with this one. So we plug in the value where the enthalpy of formation is negative 115 is equal to 339 plus 745 plus 1960 plus 248 plus minus 141 plus 791 plus lattice enthalpy here. So we have to find lattice enthalpy. So negative 115 is equal to 3945 for this one plus lattice enthalpy. So our lattice enthalpy is equal to negative 4097 kilojoule per mole. All right. Now this is for the energy cycle method. Let's look for the Born-Haber cycle. For the Born-Haber cycle, in order to do that, in order to draw the cycle, we need to remember that the positive value will go upwards and the negative value will go downwards. And this is the data given in the question. Okay, and as I mentioned, it is better to start from the enthalpy of formation of copper oxide. So it starts with the negative, so you know that you need to draw axis of enthalpy as the y-axis, and then you start up with the enthalpy of formation, which is copper solid produces copper oxide, which is in solid state also, and plus oxygen gas, and then one oxygen here, so you have to do 1/2 of oxygen gas because enthalpy of formation need to produce 1 mole of substance from its element. All right, so let's start with this one first. So copper solid plus half oxygen gas will releases energy in order to form copper oxide solid, and the release of energy is negative 115 kilojoule. All right, we settled with this equation. Now let's look at the copper first. Enthalpy of atomization of copper. So from a solid, it goes to gas, and it increased to 339. So copper solid will become copper gas, and this one will still maintain as usual because we only changes the copper enthalpy from a solid state into a gaseous state, and this requires energy as much as 339 kilojoule. Now we need to do the first ionization energy of copper. So copper gas will become copper ion, and it release 1 mole of electron. So copper gas become copper plus ion and release 1 mole of electron, and this requires energy as much as 745. Now for the second ionization energy of copper, copper plus will become copper 2 plus, and it will release another mole of electron, and then it will become 2 mole, and this requires energy as much as 1960 kilojoule. All right, so now we have done with the copper part. Now we focus on the oxygen part. Okay, atomization of oxygen. So from oxygen molecule, we need to convert that into oxygen atom. So enthalpy of atomization of oxygen. Okay, so molecule become oxygen, and oxygen atom, and this require energy as plus 248 kilojoule. And then the oxygen will receive 1 electron, which is the first electron affinity. So from neutral state, it will become a negative oxygen ion. Okay, so it will drop to 141. All right, negative copper 2 plus become O minus ion because it received 1 electron here. So it will become negative 141 kilojoule. And then the oxygen will then receive another electron, second electron affinity, but now it will increase by 791. So it will increase by 791 copper 2 plus plus O2 minus. So 791. All right. So we have settled with the information given here. And as I mentioned, lattice energy is from the gaseous ion which is forming back into a solid state. So lattice enthalpy from gaseous ion, for example, M plus ions plus X minus in the gaseous state, it will form an ionic solid. So this is known as the lattice energy. So we have to draw a line from the gaseous into the ionic solid here. And this is known as the energy lattice or lattice enthalpy or lattice energy. All right. And then according to Hess law, A to B to C to D to E to F to G to H is the same as A going to H. Okay, so AH, which is a single step, A going to H, is the same as A going to B, going to C, going to D, going to E, going to F, going to G, going to H. Okay, so A, B, C, D, E, F, G, H. So according to Hess law, the energy change in a single step is the same as in the series of steps. All right. So as long as the final is the initial is the same as the final, then the energy change going to be the same. So we can say that the enthalpy of formation, which is here, is the same as from there to there. All right. So delta HF is equal to enthalpy of atomization of copper plus ionization energy 1 plus ionization energy 2 plus atomization energy of the oxygen, electron affinity 1 and electron affinity 2 for the oxygen, as well as the lattice enthalpy here. So if you were to write at negative enthalpy, which is negative 155, I'm sorry, Okay, negative 155 is equal to the energy change of the copper, which is 339 plus 745 plus 1960 plus 248 plus minus, because it's negative here, so minus 141 plus 791 plus lattice enthalpy. So we will get negative 115 equal to 39442 plus delta H lattice. Alright, so we need to find the delta and the enthalpy lattice, which is equal to negative 4097 kilojoule per mole. So the answer that you got from the previous method, which is energy cycle method, and the Born-Haber cycle method is the same. Okay, it's just the way that you construct it going to be different. And remember, for the Born-Haber cycle, it is important to show that there is a difference in gap. For example, 155 gap is smaller compared to 339. And for 1000, as what you can see here, the gap is bigger than 700 here. Okay, so for the Born-Haber cycle, remember, positive value go upwards, negative value go downwards. And the gap need also to be distinguished. All right, so I think that's all for today's video. So hopefully you find that one helpful, and see you again some other time. Bye.